Let us start first module of chapter 3. In fact, in this chapter we shall discuss different kinds of separability property. One separability property we have already discussed, which is called Hausdorff property. A topological space is called Hausdorff if any two distinct points can be separated by disjoint open sets. In this chapter, we will examine this type of separation properties. These are very important in the context of investigation of which topological spaces are metrizable space. In fact, we will prove that with some separation property, every second countable space will be metrizable. We will also try to investigate some necessary conditions of metrizability. These separability axioms, separability chapters, investigation on separability is in fact needed for examining or for finding necessary sufficient conditions of metric spaces, and also needed to get rich source of continuous functions. We have already introduced the notion of Hausdorff property. T1 property is also a separation property in topological spaces, which we have introduced earlier. In fact, it can be easily observed that a space X is T1 if and only if for any distinct points there exists open sets such that each contains one but not the other. This is equivalent to saying that every finite set is closed. In this section, we shall introduce some other stronger separation axioms. Definition: a T1 topological space X is said to be regular if for any point X in capital X and a closed set K not containing small x, there exist disjoint open sets U and V such that X belongs to U and capital K is contained in V. Regular space is also called T3. That means a regular space is that where a point and a closed set can be strongly separated. It is easy to observe that every regular space is Hausdorff. In fact, as every regular space is T1, singleton set is closed. So, if we take two different points, we will be able to separate them strongly by disjoint open sets. Hence, every regular space is Hausdorff. We already know that every Hausdorff space is T1. So, we get regularity imply Hausdorffness imply T1ness. Sometimes it will be better for us to use the following criteria to prove the regularity. Let X be a T1 topological space, then X is regular if and only if given a point X of capital X and a neighborhood U of X, there exists a neighborhood V of X such that X belongs to V contained in V bar is subset of U. That means every neighborhood contains a closed neighborhood. To prove this theorem, let capital X be a T1 space which is regular, and consider an open neighborhood U of X. Then K is equal to X minus U is a closed set not containing X. Then by the definition of regularity, there exist disjoint open sets, say U, say V and W, such that X belongs to V and X minus U is contained in W. Now by simple calculation we can show that there exists an open set, say capital A, such that X belongs to A is contained in A bar is contained in U. That is, we can find a closed neighborhood contained in U. For the converse, let the given hypothesis be true, and we have to prove that if X is a point and K is a closed set not containing the point X, then we can separate it by disjoint open sets. Now since X does not belongs to K, so X belongs to X minus K, and X minus K is an open set. Therefore, by regularity criteria, we get an open set V such that X belongs to V is contained in V bar is contained in X minus U. So V is an open set containing X, and X minus V bar is an open set containing K, and these two open set are disjoint. This completes the proof. Next, we will show that regularity is also a hereditary property. That means we will show that every subspace of a regular space is regular. Let us take Y as a subspace of a regular space X. Now let us take X be a point and U be an open neighborhood of X in capital Y. Now since Y is a subspace of capital X, then there exists an open set O in capital X such that U is equal to O intersection Y. Then by the regularity property, there exists an open set V such that X belongs to V is contained in V bar is contained in O. Let us take the trace of V on Y. Then V intersection Y is an open set in Y, and V intersection Y closure in Y is equal to closure of V in X intersection Y. Hence, we get that X belongs to V intersection Y subset of closure of V intersection Y in Y subset of U. This proves that Y is regular. Hence, regularity is a hereditary property. Next, we will prove that product of Hausdorff spaces is Hausdorff and product of regular spaces is regular. Let us first prove that product of Hausdorff spaces is Hausdorff. For this, let us consider X alpha be a collection of Hausdorff spaces, and let X be the product of X alpha. Let us choose two distinct points x and y in product of x alpha. Then there should exist some coordinate alpha such that x alpha not equal to y alpha. Now, since x alpha is a Hausdorff space, then there exist disjoint open sets U alpha and V alpha containing x alpha and y alpha respectively. Let us take pi alpha inverse U alpha and pi alpha inverse V alpha. Then x belongs to pi alpha inverse U alpha and y belongs to pi alpha inverse V alpha, which are subbasic open sets of the product topology and disjoint. Therefore, product of x alpha is a Hausdorff space. Next, we prove that if each x alpha is regular, then product of x alpha is also regular. First, since regular space are T1, then each x alpha is T1. Since it is easy to prove that product of T1 spaces is T1, so product of x alpha is T1. Now, we have to prove that product of x alpha satisfies the regularity criteria. We will use the regularity criteria in the following ways. Let B is equal to product of U alpha be a basic open set containing a point x, then there exist finitely many coordinate alpha 1, alpha 2, alpha n such that U alpha is equal to x alpha for all alpha not equal to alpha 1, alpha 2, alpha n. Then for each alpha I there exist open sets Vi in Xi such that Xi belongs to Vi is contained in Vi bar is contained in U alpha I by the regularity property of X alpha I. Let us take V is equal to product of V alpha. Alpha belongs to the index set. We know that product of V alpha closure is equal to closure of product of V alpha. This proves that X belongs to V subset of closure of V is contained in U, which satisfy the regularity property. Therefore, product of X alpha is regular and we have already got T1ness. Next, we shall prove an existence of a topological space which is Hausdorff but not regular. The theme of the example is that we will use R with its usual topology and take a closed set of R in the usual topology and retopologize it in such a way that some closed set become open in the new topology. For this, let us recall the K topology we have introduced earlier. Let K is equal to 1 by n such that n belongs to capital N, and consider the subset open interval a b minus k, that is all points in the open interval a b such that a b not equal to 1 by n for any integer n belongs to n. Then the collection all open interval a b such that a b belongs to R union open interval a b minus k such that a b belongs to R is a basis for some topology on R, it can be proved that K is the closed set in the new topology, but 0 cannot be strongly separated from this K. So, in the K topology, closed set and point cannot be strongly separated, and therefore, K topology is not regular. But since this is finer than the usual topology R, this is obviously Hausdorff. Another example can be constructed in the way that, let us take the usual topology on R and let us consider also Q as open set. Now, usual topology on R with Q become a subbase for some topology. So, from this subbase we can generate a topology. In this new topology, the closed set Q cannot be separated from any irrational number. So, this topology is also an example of a Hausdorff space which is not regular. We know that R is a metrizable space. In fact, we show that every metrizable space is regular. For this, we shall need a metric space version of famous Eurytion's lemma. The original Eurytion's lemma we will state and prove later, but here let us state the metric space version of Eurytion's lemma. Let capital F be a closed set of a metric space X and G is an open set containing F. Then there is a continuous function f from x to r such that f(x) less or equal to 1 greater or equal to 0 for all x in capital X, and f(x) is equal to 1 when x belongs to x and f(x) is equal to 0 when x belongs to capital X minus z. For the proof, take f of x is equal to d of x capital X minus z by d of x f plus d of x capital X minus z. Now assume we have a metric space x d. If capital F is closed and x does not belongs to capital F, then capital F and singleton set x are disjoint closed sets. By the above lemma, there is a continuous function f from x to r such that f(x) is equal to 1 and fy is equal to 0 for every y in capital F. Hence, if u is equal to all those y in capital X such that fy greater than 1 and v is equal to all y belongs to capital X such that fy strictly less than 1, then they are disjoint open sets separating X from F. This shows that every metric space is regular space. So, still now we have discussed basically two separation properties, Hausdorffness and regularity. Next, we will discuss another important separable property which is called normality. So, let us define what is called normality, or let us define normal space. A T1 topological space X is said to be normal if for any two disjoint closed sets H and K there exist disjoint open sets U and V such that H is contained in U and K is contained in V. Normal space also called T4 spaces. Now, it is easy to prove that every normal space is regular. In fact, let X be a normal space and let small x belongs to capital X and K be a closed set not containing X. Since capital X is normal, then it is obviously T1. So, singleton set is closed. So, we have two closed sets, singleton set closed set X and capital K. Then we can separate them by disjoint open sets U and V by the definition of normality. Hence, the space become regular. We shall prove in future that there exist regular spaces which are not normal. Next, we present a criteria for determining normal property. Lemma, let X be a T1 topological space, then X is normal if and only if given a closed set K of X and an open set U containing K, there is an open set V such that K is contained in V, is contained in V bar, is contained in U. Let X be a T1 space which is normal and consider an open set U containing K. Then H is equal to X minus U is a closed set disjoint from K. Now we have to use the definition for the proof. For the converse, let the given hypothesis be true and K and H be disjoint closed sets. Then H is contained in X minus K and X minus K is open. Then choose an open set containing H contained in X minus K with its closure. Let us give an example of a normal space. In fact, our Sorgenfrey line is an example of a normal space. Since the topology of RL is finer than that of RU, it is immediate that singleton sets are closed in RL. Now, to check the normality, suppose that A and B are two disjoint closed sets in RL. For each point A of capital A, choose a basis element AXA not intersecting capital B, and for each point B of capital B, choose a basis element BXB not intersecting capital A. Now consider open sets U is equal to union of AXA such that A belongs to A and V is equal to union BXB such that B belongs to capital B. Then clearly capital A is contained in U and capital B is contained in V. Now, if U and V meets, then there exists a point Z which belongs to the intersection of some AXA and BXB, which gives us a contradiction. So, Sorgenfrey line is a normal space. Quite similarly, we can prove that every metrizable space is also normal. Let capital X be a metrizable space and consider two disjoint closed sets A and B. For each A belongs to capital A, choose RA such that BA RA by 2 does not meet capital B. Similarly, for each B in capital B, choose RB so that the ball B RB does not meet A. Now define U is equal to union of B A RA by 2, where small a belongs to capital A and V is equal to union capital B B RB such that small b belongs to capital B. Then U and V are open sets containing A and B respectively. Now, if Z belongs to U intersection V, then there exists some A belongs to capital A and B belongs to capital B such that Z belongs to capital B A RA by 2 intersection capital B small b RB by 2. By triangle inequality, therefore, we have D of AB strictly less than RA plus RB by 2. If RB less or equal to RA, then DAB strictly less than RA, so that the open ball BARA contains the point B, a contradiction. Hence, U and V are disjoint. So, in this module, we have discussed three separation properties: Hausdorffness, regularity and normality. We have produced an example of Hausdorff space which is not regular, and we have shown that Hausdorffness, regularity are productive properties. In the next module, we shall present an example of a regular space which is not normal, and we shall also discuss about the productive property of normal spaces. We shall also show that ordered topological space are also normal.